Imagine for a moment that you're lying beneath a vast starry sky. The cool air brushes against your skin as you look up at the twinkling lights above. The night sky has always had a way of captivating our attention, hasn't it? That feeling of wonder, of mystery, has been with humanity for as long as we've existed. We've always been drawn to the unknown, trying to make sense of it. And the universe, with all its secrets, is perhaps the greatest mystery of all. Think of the universe like a giant book. But unlike any book you've ever read, this one has no clear beginning, no defined end, and each page seems more bewildering than the last. What we know, what we've discovered, is but a few chapters within a vast and endless tome, filled with stories yet untold, mysterious unsolved, and truths that seem just out of reach. And at the center of this book is a question that has haunted philosophers, scientists, and dreamers alike. Why does the universe exist at all? It's a simple question on the surface, but the more you think about it, the deeper it pulls you in. Why is there something rather than nothing? It's a question that lies at the heart of everything we know, or rather everything we don't know. When you sit with this question, it's easy to feel the weight of its enormity. We're small, fragile beings trying to comprehend a reality that stretches far beyond what we can see or touch. This is where the concept of the eternal mystery of the universe comes into play. The universe, in all its vastness, operates on scales of time and space that are nearly impossible to grasp. It's old, so old that our human minds struggle to comprehend the sheer magnitude of its age, billions of years. But even that number doesn't do it justice. What does a billion years feel like? How do you quantify something that existed long before life as we know it ever began, and will continue to exist long after we're gone? It's like trying to imagine the length of a road that stretches endlessly in both directions. You know it's there. You know it continues. But there's no way to see the end of it. No way to truly understand its full scope. The mystery isn't just in its vastness, but in its persistence. The universe seems timeless, eternal, always there, yet always just beyond the limits of our understanding. Consider this. If you zoomed out far enough, beyond our solar system, beyond our galaxy, beyond the clusters of galaxies that form the cosmic web, you'd still only be seeing a fraction of the whole. No matter how far you go, no matter how much you learn, there's always more to uncover. More stars, more planets, more strange phenomena that challenge the very fabric of what we think we know. But here's where it gets even more interesting. The deeper we peer into the cosmos, the more we realize that we're not just looking at the universe. We're part of it. The atoms that make up your body, the elements that compose everything around you, were forged in the hearts of stars that lived and died billions of years ago. We are quite literally made of stardust. In that sense, the universe isn't just out there, separate from us. It's within us, too. This connection between the vastness of the cosmos and our own existence brings us back to the idea of the eternal mystery. We are both observers of the universe and participants in it. Our thoughts, our actions, our very existence are intertwined with the cosmos in ways we're only beginning to understand. And as much as we've learned, there's still so much that remains hidden. What lies beyond the edge of what we can see? What existed before the universe as we know it came into being? Will the universe continue on forever, or will it one day come to an end? These are questions that drive us to explore, to seek out answers, even as we know that some mysteries may never be fully solved. The eternal mystery of the universe is not something to be feared, but something to be embraced. It's a reminder that we are part of something much larger than ourselves, something that transcends the limits of our understanding. It's an invitation to keep asking questions, to keep seeking knowledge, and to remain in awe of the world around us. As you drift into sleep, let that feeling of wonder wash over you. The universe may be vast, its mysteries endless, but you are a part of it. And in that connection, there is beauty, there is meaning, and there is the promise of discovery. The cosmic microwave. Imagine you're sitting in a quiet room, the hum of electricity faint in the background, almost imperceptible. You may not notice it, but it's always there, surrounding you, an ever-present low buzz. Now imagine that hum isn't just in your room, but across the entire universe, filling the vastness of space with a faint, persistent noise. That hum is a remnant of the universe's earliest moments, an echo of the Big Bang itself. This is the cosmic microwave background, or CMB, one of the most profound and revealing discoveries in modern cosmology. To truly understand the cosmic microwave background, let's take a journey back in time. Picture the universe as it was approximately 13.8 billion years ago, when it was still an infant. Back then, the cosmos was nothing like what we see today. Instead of stars, galaxies, and planets, it was a seething hot soup of particles, protons, neutrons, and electrons, colliding with photons of light in a chaotic dance. The universe at that time was opaque, a fiery plasma where light couldn't travel far without bumping into something. It was like trying to see through the densest fog imaginable. As this primordial soup expanded, it also cooled. Around 380,000 years after the Big Bang, something extraordinary happened. The universe had cooled enough for protons and electrons to combine and form neutral hydrogen atoms. With fewer charged particles around to scatter light, the universe suddenly became transparent, and for the first time light could travel freely through space. This moment is known as recombination, and the light that was set free at that time still exists today. That light is the cosmic microwave background. Think of the CMB as a baby picture of the universe, just like a photograph of a newborn captures a moment in time. The cosmic microwave background shows us the universe as it looked when it was still in its infancy. It's an image frozen in time, giving us a glimpse into what the universe was like when it was just 380,000 years old, an instant in cosmic terms. Now, here's where it gets even more fascinating. When we observe the cosmic microwave background today, we're not just seeing a uniform glow. This ancient light is incredibly faint, but it's not perfectly smooth. Instead, it contains tiny fluctuations, minuscule differences in temperature that are only a few parts in 100,000. These temperature fluctuations are crucial because they're the seeds from which everything we see in the universe today, galaxies, stars, planets, and even us, grew. It's like looking at a pot of soup as it cools. At first, the surface might look smooth, but upon closer inspection, you notice tiny ripples and currents. These slight variations in the CMB are the result of quantum fluctuations that occurred in the very early universe, amplified by cosmic inflation, a brief period of rapid expansion that took place fractions of a second after the Big Bang. These fluctuations were the starting points for the formation of large-scale structures in the universe. Fast forward billions of years, and those tiny ripples in the CMB have evolved into the vast cosmic web of galaxies and clusters that fill the universe. The same light that was once scattered and blocked now passes through space unhindered, giving us a snapshot of the universe at a time when everything we know today was just beginning to take shape. And the CMB isn't just a pretty picture, though. It's one of the most important pieces of evidence for the Big Bang theory. When scientists first predicted the existence of this ancient radiation in the 1940s, they had no idea it would eventually be detected. But in 1965, two radio astronomers, Arno Penzias and Robert Wilson, stumbled upon it by accident. They were trying to eliminate noise from their radio antenna, but no matter what they did, They couldn't get rid of this persistent hum. It turned out that this hum was the cosmic microwave background, the very first direct evidence of the Big Bang. For their discovery, they were awarded the Nobel Prize in Physics in 1978. Today, the study of the CMB has become a cornerstone of cosmology. Space missions like the COBE, WMAP, and Planck satellites have mapped the CMB with extraordinary precision, revealing detailed information about the universe's age, composition, and evolution. From these observations, we've learned that the universe is about 13.8 billion years old, that it's composed mostly of dark matter and dark energy, and that it's flat, meaning that the geometry of space is not curved in a significant way. In essence, the cosmic microwave background is a cosmic relic, a faint glow from the birth of the universe that continues to illuminate the darkest corners of space. It's a reminder of where we came from, a time when everything we see today was packed into a hot, dense state, waiting to unfold into the universe we now call home. As you drift into sleep, let the thought of this ancient light, still traveling across the cosmos, bring you a sense of connection to the vast and mysterious universe we inhabit. Time dilation. Imagine you're in a spaceship, far from Earth, traveling near the speed of light. From your perspective, everything inside the spaceship seems normal. Time ticks by as it always has. But if you could look back at Earth, you'd notice something strange. Clocks that seem to be ticking more slowly than your own. Dies, months, and even years pass for the people on Earth while, for you, only a few hours or days have passed. This is the effect of time dilation, one of the most mind-bending consequences of Einstein's theory of relativity. To understand time dilation, you have to first rethink what time and space really are. We often think of time as this universal, steady tick-tock that affects everything equally, no matter where you are or how fast you're moving. But in Einstein's view, time isn't a fixed, universal constant. It's relative, changing, depending on how fast you're moving and where you are in a gravitational field. Space and time are woven together into a single fabric, called spacetime. And when you move through space, it affects how you experience time. Think of spacetime as a flexible sheet, like a trampoline. If you stand still in the middle of the trampoline, the sheet is smooth and flat. But if you start moving across it, you stretch and bend the sheet beneath your feet. The faster you move, the more you distort the sheet. And this distortion affects the way time flows. If you're moving very fast, near the speed of light, this effect becomes extreme, so much so that what feels like a few hours to you could be years, even centuries, for someone who's standing still. The famous twin paradox illustrates this idea beautifully. Imagine you have two identical twins. One stays on Earth, while the other boards a spaceship and travels near the speed of light. After a long journey, the spacefaring twin returns to Earth. But when the two meet again, something astonishing has happened. The twin who stayed on Earth has aged much more than the one who traveled through space. The space traveler has experienced time at a slower rate. Years have passed for the Earth twin, but only a short amount of time for the spacefaring twin. This isn't science fiction. It's a real prediction of Einstein's theory of relativity, and experiments have shown that this effect actually happens even at much lower speeds than light. One of the most famous examples of time dilation comes from experiments with atomic clocks. These clocks are incredibly precise, and they're used to test the effects of time dilation in real-world situations. In one experiment, scientists took two atomic clocks, synchronized them perfectly, and then flew one of them around the Earth on a fast-moving airplane while the other stayed on the ground. When the traveling clock returned, it was slightly behind the stationary clock. Time had passed more slowly for the clock on the airplane because it was moving faster. This experiment confirmed Einstein's predictions and showed that time dilation isn't just a theoretical idea, it's a measurable reality. But time dilation doesn't just happen because of speed. Gravity also affects time in a similar way. According to Einstein's theory of general relativity, massive objects like planets and stars create curves and dips in the fabric of space-time. The stronger the gravity, the more space-time is warped, and the more time is affected. Near a massive object like a black hole, time would slow down dramatically compared to a place with weaker gravity. This is why, theoretically, if you were to approach the event horizon of a black hole, where gravity is at its strongest, time would slow down to a near standstill relative to the outside universe. To put this in more concrete terms, imagine standing on the surface of a very dense, massive planet. Because the planet's gravity is much stronger than Earth's, time would pass more slowly for you than for someone far away from the planet. If you lived there for a while and then returned to Earth, you might find that many more years had passed on Earth than you had experienced on the massive planet. This isn't just hypothetical. Astronauts aboard the International Space Station, which orbits Earth at high speeds and experiences slightly weaker gravity than we do on the surface, actually experience time a tiny bit slower than we do. The difference is minuscule, but it's real. Time dilation forces us to rethink our very understanding of time. It's not just a steady beat that marches forward the same way for everyone, everywhere. Time is fluid, affected by speed and gravity, bending and stretching as you move through the universe. In a way, time dilation reveals the hidden flexibility of the cosmos, showing us that even something as fundamental as time isn't as straightforward as it seems. As you think about the vastness of space and the mysteries of time, consider this. The universe is constantly shifting, warping, and bending in ways that defy our everyday experience. Time dilation is just one piece of this puzzle, a reminder that the universe operates on scales and principles that are often beyond our immediate comprehension. Yet, through the lens of relativity, we gain a glimpse into the strange and wonderful nature of time and space, and the profound ways they are interconnected. Dark energy. Imagine you're holding a balloon in your hands. You slowly blow air into it, watching as the balloon expands outward in every direction. Now imagine that this balloon represents our universe. Just as the balloon stretches and grows, so too does our universe, expanding outward over time. But here is the twist. Something is fooling this expansion, and not just at a slow, steady pace. The universe is expanding faster and faster as time goes on, as if someone is continually pumping more air into the balloon. This mysterious force driving the accelerating expansion of the universe is what we call dark energy. Dark energy is one of the most perplexing concepts in modern cosmology. If dark matter is like an invisible glue holding galaxies together, dark energy is more like a cosmic wind pushing everything apart. It's counterintuitive. While gravity should be pulling things together, dark energy seems to be working in the opposite direction, driving galaxies away from each other at an ever-increasing speed. In fact, dark energy makes up about 70% of the total energy content of the universe, which means that the vast majority of what makes up the cosmos is something we can't see, touch, or even fully understand. The discovery of dark energy came as a shock to scientists. In the late 1990s, two teams of astronomers were studying distant supernovae, massive explosions that mark the deaths of stars. These supernovae are incredibly bright, and because they all explode with roughly the same intrinsic brightness, they act as standard candles for measuring distances in the universe. By comparing the observed brightness of a supernova with its actual brightness, astronomers can calculate how far away it is. When the two teams analyzed their data, they found something unexpected. The supernovae were dimmer than they should have been if the universe's expansion was slowing down, as most scientists had assumed. Instead, the universe's expansion was speeding up. This was the opposite of what gravity alone would predict, and it implied that some unknown force, dark energy, was driving this acceleration. To get a sense of how strange this is, imagine you throw a ball into the air. Normally, gravity would slow the ball down, eventually pulling it back to Earth. But what if, instead of slowing down, the ball suddenly sped up and flew off into the sky, accelerating faster and faster the farther it got from you? That's essentially what dark energy is doing to the galaxies in the universe. Instead of slowing down due to gravity, they're being pushed apart by this mysterious force. Dark energy isn't just a small player in the cosmos. It dominates the universe. As space itself expands, dark energy's influence grows stronger. It's as if the more the universe expands, the more dark energy there is, fueling the expansion even further. This creates a feedback loop, where the expansion of space generates more dark energy, which in turn accelerates the expansion even more. It's a runaway effect that has profound implications for the future of the universe. One of the most baffling questions about dark energy is what exactly it is. There are several theories, but no definitive answers. Some scientists believe that dark energy could be a property of space itself, a kind of vacuum energy that arises from the very fabric of the universe. Others suggest that it might be a new kind of field or particle, something completely unlike anything we've ever encountered before. Yet another theory is that dark energy could be related to Einstein's cosmological constant, a term he added to his equations of general relativity to allow for a static universe. When Einstein later learned that the universe was expanding, he famously called the cosmological constant his biggest blunder and removed it from his equations. But with the discovery of dark energy, some scientists think that Einstein's constant might not have been such a blunder after all. It could be that this constant represents the energy of empty space, driving the universe's accelerated expansion. As strange as dark energy is, its implications are even more unsettling. If dark energy continues to dominate the universe, then the future of the cosmos could be quite bleak. In the distant future, billions or even trillions of years from now, the universe could become a cold, dark, and lonely place. As galaxies move farther and farther apart, the stars within them will burn out, and the universe will drift into a state of eternal expansion, where everything is so spread out that nothing can interact with anything else. It's a scenario known as the Big Freeze, where the universe continues expanding forever, but becomes increasingly empty and lifeless. So as you lay back and let your thoughts drift into the vastness of space, consider the enigma of dark energy. It's a reminder that, despite all our knowledge and understanding, there are still profound mysteries lurking in the cosmos. Dark energy is the invisible hand guiding the universe's future, a force that defies our expectations and challenges our understanding of reality itself. As you drift off to sleep, let the thought of this mysterious force guide your dreams, expanding your imagination just as it expands the universe, pushing the boundaries of what we know and what we have yet to discover. Dark matter. Picture yourself walking through a dense forest at twilight. The trees around you are tall and imposing, but you can only see a few feet ahead. There's an eerie quiet, punctuated by the occasional rustling of leaves. You know the forest is full of life. Birds, insects, maybe even larger animals, but you can't see them. You can only feel their presence, hear the subtle signs of movement, and infer their existence through the disturbances they create. Dark matter in the universe is much like those unseen creatures in the forest. It's an invisible force, something we cannot observe directly. But we know it's there because of the way it influences the world around it. Dark matter is one of the most perplexing and mysterious components of the universe. Unlike the stars, planets, and galaxies we can observe, dark matter doesn't emit, absorb, or reflect any form of light or electromagnetic radiation. It's completely invisible to our telescopes. Yet it makes up roughly 85% of the total mass of the universe. This means that the vast majority of the universe is composed of something we've never directly seen. We know dark matter exists because of the effects it has on the visible matter around it. One of the earliest clues came from observing the movement of galaxies. In the 1930s, astronomer Fritz Zwicky noticed that galaxies in clusters were moving much faster than they should be, based on the amount of visible matter. These galaxies were behaving as if there was some unseen mass pulling on them with an enormous gravitational force. Zwicky called this unseen mass Dunkel Materia, or dark matter. Later, in the 1970s, astronomer Vera Rubin provided even more compelling evidence. She studied the rotation curves of spiral galaxies and found that the outer stars in these galaxies were moving just as fast as the stars near the center. According to the laws of physics, the outer stars should have been moving more slowly, like planets in our solar system that orbit more slowly the farther they are from the sun. The only explanation for this discrepancy was that there must be some invisible mass, dark matter, surrounding the galaxy and providing extra gravitational pull. Think of a merry-go-round. If all the mass was concentrated at the center, the horses on the outer edge would move much more slowly than those near the middle. But if there were an unseen force, like an invisible person pushing each horse equally, they would all move at the same speed. Dark matter is that unseen force in galaxies, holding everything together and preventing them from flying apart. Dark matter doesn't just affect galaxies, it plays a fundamental role in the large-scale structure of the universe. Over billions of years, dark matter has shaped the formation and evolution of galaxies and galaxy clusters. Imagine sprinkling grains of sand across a surface. If there were an invisible magnet under that surface, the grains would clump together in certain pattern, attracted by the magnetic force. Similarly, dark matter acts like a cosmic magnet, drawing visible matter into dense regions and influencing the formation of galaxies, stars, and planets. Scientists have even mapped out the distribution of dark matter across the universe by studying gravitational lensing. This phenomenon occurs when light from a distant galaxy is bent by the gravitational pull of a massive object, such as a cluster of galaxies, along its path. By measuring how much the light is bent, astronomers can infer the presence of dark matter, even though they can't see it directly. This has revealed vast webs of dark matter stretching across the cosmos, forming the scaffolding on which galaxies are built. Despite all we know about its effects, dark matter remains one of the greatest mysteries in modern physics. What is it made of? Is it composed of some unknown particle that doesn't interact with light? Could it be something even more exotic, like primordial black holes or some other form of matter we haven't yet discovered? Scientists around the world are conducting experiments to detect dark matter particles directly, deep underground, in specially shielded detectors. But so far, these efforts have yielded no definitive answers. As you lie back and let your mind wander through the vastness of space, imagine the unseen web of dark matter stretching across the universe, silently shaping the galaxies and stars. It's a reminder that even in the most well-explored regions of science, there are still profound mysteries waiting to be uncovered. Dark matter challenges our understanding of the cosmos, urging us to look beyond the visible and question the nature of reality itself. In the silence of the night, as you drift off to sleep, let the mystery of dark matter envelop you, an invisible force guiding your dreams across the universe. Quasars, magnetars. Imagine holding a powerful magnet in your hand, one so strong that it could pull metal objects from across the room. Now magnify that strength by billions, even trillions of times, and you'll begin to approach the power of the most magnetic objects in the universe, magnetars. These extraordinary stars defy comprehension. Their magnetic fields so intense that they can distort atomic structures, causing matter to behave in ways that defy the laws of physics as we know them. Magnetars are a type of neutron star born from the violent deaths of massive stars in supernova explosions. Like all neutron stars, they are incredibly dense, so dense that a sugar cube-sized amount of their material would weigh as much as a mountain on Earth. But what sets magnetars apart from regular neutron stars is their mind-bendingly strong magnetic fields, which can be 1,000 times stronger than that of a typical neutron star, and up to a quadrillion times stronger than Earth's magnetic field. To put this in perspective, if a magnetar were located halfway between the Earth and the Moon, its magnetic field would be strong enough to wipe the data from every credit card on Earth. It would also disrupt electronics, induce massive currents in power lines, and wreak havoc on our planet's magnetic field. Thankfully, magnetars are rare, and the closest known one is about 9,000 light-years away, far enough to spare us from its devastating effects. The origin of a magnetar's magnetic field is a mystery, but one leading theory is that it arises during the star's formation. When a massive star collapses into a neutron star, it retains much of its angular momentum, causing it to spin rapidly. This rapid rotation, combined with the intense gravitational collapse, can amplify the star's magnetic field to unimaginable levels. Over time, as the magnetar loses energy, it slows down, but its magnetic field remains extraordinarily strong. Magnetars are not just curiosities of extreme physics. They are also among the most violent objects in the universe. Their magnetic fields can cause starquakes, sudden shifts in the star's crust that release immense amounts of energy in the form of high-energy radiation, including X-rays and gamma rays. These starquakes are the most powerful explosions known to occur in our galaxy, second only to supernovae. In 2004, a burst of gamma rays from a magnetar located about 50,000 light-years away was so intense that it briefly ionized Earth's upper atmosphere, even though the magnetar was on the other side of the galaxy. This event, known as the SGR 1806-20 flare, released more energy in a fraction of a second than the Sun emits in 100,000 years. Had the magnetar been located just a few light-years away, the radiation would have caused significant damage to our planet's atmosphere, potentially leading to mass extinction. Thankfully, such events are extremely rare, and most magnetars are located far from Earth. Magnetars also challenge our understanding of matter and the fundamental forces of nature. Under the influence of a magnetar's magnetic field, atoms are stretched into pencil-thin shapes, their electron clouds distorted. The laws of quantum mechanics, which govern the behavior of matter at the smallest scales, begin to break down under such extreme conditions. This makes magnetars natural laboratories for studying the limits of physics and the behavior of matter under conditions that cannot be replicated on Earth. These stars are also shrouded in mystery. We know of only about 30 magnetars in our galaxy, but there could be many more hidden among the vast sea of stars. Their fleeting bursts of radiation make them difficult to study, and much of what we know about them comes from brief, intense events rather than prolonged observation. Some scientists believe that magnetars may be responsible for phenomena known as fast radio bursts, brief, powerful flashes of radio waves that originate from distant galaxies. These bursts are still poorly understood, and magnetars are one of the leading candidates for their origin. Despite their rarity, magnetars have a profound impact on their surroundings. Their magnetic fields can influence nearby stars and gas clouds, shaping the environment around them. They are cosmic engines of destruction and creation, tearing apart matter with their magnetic fields, while also seeding the universe with elements produced in their violent births. As you let your mind wander and drift into sleep, imagine a star that defies the ordinary, a star so powerful that it reshapes the very fabric of reality around it. Magnetars, with their colossal magnetic fields and violent starquakes, are a reminder of the universe's extremes, where the rules we take for granted no longer apply. These enigmatic stars push the boundaries of our understanding and offer a glimpse into the untamed forces that govern the cosmos. Pulsars. Imagine standing on the edge of a vast ocean at night, with nothing but the stars above and the dark water below. In the distance, a lighthouse emits a steady beam of light, sweeping across the horizon at regular intervals, guiding ships through treacherous waters. Now, picture this lighthouse as an astronomical object, its beam traveling through the vastness of space, not guiding ships, but sending signals across the universe. This is the essence of pulsars, cosmic lighthouses created by nature. Pulsars are a special type of neutron star, born from the explosive death of massive stars. When these stars run out of fuel, they collapse under the force of gravity, and if the remaining core is compact enough, it forms a neutron star. But unlike regular neutron stars, pulsars have a unique feature. They emit beams of electromagnetic radiation from their magnetic poles. These beams of radiation are so intense that they can be detected across vast distances in space. What makes pulsars particularly fascinating is their rotational speed. As the original massive star collapses into a neutron star, it conserves angular momentum, causing the newly formed pulsar to spin at incredibly high speeds. This is similar to how an ice skater spins faster when pulling their arms in close to their body. Some pulsars rotate hundreds, even thousands of times per second. As they spin, their magnetic fields generate these beams of radiation. And when these beams sweep across Earth, we detect them as regular pulses of radio waves, X-rays, or even gamma rays. The precision of these pulses is astonishing. Pulsars are some of the most accurate natural clocks in the universe. In fact, certain pulsars are so consistent in their timing that they rival the precision of atomic clocks. The regularity of their pulses can be used to measure time with incredible accuracy, making pulsars cosmic timekeepers. Scientists have even used pulsars to study gravitational waves and map the interstellar medium. But why do pulsars emit these beams of radiation? The answer lies in their intense magnetic fields. Pulsars are like gigantic electromagnets with magnetic fields billions to trillions of times stronger than Earth's. As the pulsar spins, these magnetic fields accelerate charged particles near the star, creating beams of electromagnetic radiation that shoot out from the magnetic poles. If the pulsar's magnetic poles are not aligned with its rotational axis, the beams will sweep across space, much like the light from a rotating lighthouse. The discovery of pulsars was one of the most exciting astronomical events of the 20th century. In 1967, Jocelyn Bell Burnell, a graduate student at Cambridge University, noticed a series of regular pulses in the data from a radio telescope. These pulses were so regular that at first, she and her colleagues thought they might be signals from an extraterrestrial civilization. They even jokingly called the source LGM1, which stood for Little Green Men. However, it soon became clear that the pulses were not from aliens, but from a previously unknown type of neutron star, what we now call pulsars. One of the most famous pulsars is the Crab pulsar, located in the heart of the Crab Nebula, a supernova remnant about 6,500 light-years from Earth. The Crab pulsar rotates 30 times per second, and its pulses of radiation can be detected across the electromagnetic spectrum, from radio waves to gamma rays. The crab pulsar is a vivid reminder of the violent death of a massive star, and its regular pulses serve as a cosmic metronome, ticking away in the vast expanse of space. Pulsars come in different varieties, depending on their rotational speed and the type of radiation they emit. Some pulsars, known as millisecond pulsars, rotate hundreds of times per second and are thought to have been spun up by accreting matter from a companion star. Others, known as magnetars, have magnetic fields so intense that they can cause a star quarkus, violent shifts in the star's crust that release bursts of high-energy radiation. These different types of pulsars showcase the diversity of these cosmic lighthouses and the extreme physics that governs them. Beyond their role as cosmic clocks, pulsars also provide valuable insights into the fundamental nature of matter and the forces that govern the universe. Because they are so dense, pulsars allow scientists to study the behavior of matter under conditions that cannot be replicated on Earth. The interior of a pulsar is a mystery, with theories ranging from exotic forms of matter, such as quark gluon plasma, to strange matter, where the usual distinctions between particles break down. Pulsars, with their precise pulses and extreme conditions, serve as natural laboratories for studying the laws of physics in the most extreme environments. They challenge our understanding of the universe and offer glimpses into the violent and dynamic processes that shape the cosmos. As you close your eyes and drift off to sleep, imagine the steady pulse of a distant pulsar spinning relentlessly in the vastness of space. Like a cosmic heartbeat, it pulses through the darkness, a reminder of the strange and beautiful universe that surrounds us. These cosmic lighthouses, though far away, connect us to the mysteries of the stars and the unimaginable forces that govern our existence. Neutron stars. Imagine crushing the entire mass of the Sun, roughly 330,000 times the mass of Earth, into an object no larger than a small city. This mind-bending density is what makes neutron stars some of the most fascinating and extreme objects in the universe. Born from the explosive death of a massive star, these cosmic remnants defy the imagination, revealing the strange and incredible forces at play in the cosmos. Neutron stars are the densest known objects in the universe that are still visible to us. To understand how dense they truly are, picture this. A single teaspoon of neutron star material would weigh about 1 billion tons on Earth. This unfathomable density is a result of the way neutron stars are formed. When a massive star exhausts its nuclear fuel and undergoes a supernova explosion, its core can collapse under the force of gravity. If the core is between about 1.4 and 3 times the mass of the Sun, it doesn't form a black hole, but instead becomes a neutron star. During the collapse, protons and electrons in the star's core are squeezed together so tightly that they combine to form neutrons, leaving behind an object composed almost entirely of neutrons. The result is a dense sphere with a diameter of about 20 kilometers, or roughly the size of a city like Manhattan. But the story of neutron stars doesn't end with their incredible density. These objects also possess some of the most extreme physical properties in the universe. For one, they have incredibly strong magnetic fields, trillions of times stronger than Earth's magnetic field. This powerful magnetism can lead to extraordinary phenomena, such as the emission of intense beams of radiation that can be detected as pulsars. Pulsars are a special type of neutron star that rotate at astonishing speeds, often hundreds of times per second. As they spin, their magnetic fields generate beams of radiation that sweep across the sky like cosmic lighthouses. When these beams happen to be pointed toward Earth, we observe regular pulses of radiation, which is how pulsars got their name. The precision of these pulses is so accurate that some pulsars are used as cosmic clocks, with their timing rivaling the precision of the best atomic clocks on Earth. The rotation of pulsars is another remarkable feature of neutron stars. These objects conserve the angular momentum of the original star, which means that as they shrink in size, they spin faster, much like a figure skater pulling in their arms during a spin. Some pulsars rotate hundreds or even thousands of times per second. The fastest known pulsar, PSRJ 1748-2446 AD, spins at a mind-boggling 716 times per second. This incredible speed, combined with the neutron star's density, makes it one of the most extreme objects known to science. But neutron stars are more than just dense and fast-spinning objects. They are also key players in some of the universe's most violent events. When four neutron stars orbit each other in a binary system, their immense gravity causes them to gradually spiral toward each other. When they eventually collide, the energy released in the explosion can be enormous, leading to what's known as a kilonova. These collisions also produce gravitational waves, ripples in space-time that were first detected on Earth in 2017, confirming a major prediction of Einstein's theory of general relativity. Neutron star mergers are also thought to be responsible for creating some of the universe's heaviest elements, such as gold and platinum. When these stars collide, the energy released is so great that it can forge these heavy elements and scatter them across space. This means that the gold in your jewelry or the platinum in your electronics likely originated in the cataclysmic merger of two neutron stars billions of years ago. Despite their extreme properties, neutron stars are not easy to find because they are so small and dense. They don't emit much light, making them difficult to detect with traditional telescopes. Most of what we know about neutron stars comes from observing pulsars and detecting gravitational waves from neutron star mergers. However, as our technology improves, we're continuing to learn more about these fascinating objects and their role in the universe. As you drift into sleep, think about the strange and beautiful universe that surrounds us. Somewhere out there, beyond the reach of our telescopes, neutron stars are spinning at incredible speeds, emitting pulses of radiation across the cosmos, and waiting for the day when they might collide in a spectacular explosion. These cosmic enigmas remind us that the universe is full of surprises, and that even the most extreme and improbable phenomena are a natural part of the cosmic story. Supernovae. Picture a star, a giant glowing orb in the sky, billions of miles away, holding itself together through a delicate balance. For millions, sometimes billions of years, this star burns brightly, fusing hydrogen into helium in its core, producing light and heat. But for some stars, especially the most massive ones, there comes a time when this balance is disrupted. The star can no longer sustain itself, and in its final dramatic moments, it undergoes one of the most violent events in the universe. A supernova. A supernova is not just the death of a star. It's a cosmic explosion of unimaginable power, a firework display on a galactic scale. The light from a single supernova can outshine an entire galaxy for a brief period. In fact, when one happens close enough to Earth, it can be visible in the night sky with the eye, even during the day. But what causes such a powerful event? To understand a supernova, imagine a star as a vast nuclear reactor. In its core, nuclear fusion converts hydrogen into helium, producing the energy that makes the star shine. This fusion creates an outward pressure that counteracts the force of gravity, trying to collapse the star. For most of its life, the star remains stable, but as it ages and consumes more of its fuel, this balance begins to falter. When a massive star reaches the end of its life, it runs out of hydrogen and starts fusing heavier elements like carbon, oxygen, and eventually iron. But iron is different. Instead of releasing energy when it fuses, iron absorbs energy. At this point, the star's core becomes unstable, without energy being produced to push back against gravity. The core collapses in on itself in a fraction of a second. This collapse triggers a shock wave that travels outward, tearing the star apart in a colossal explosion. A supernova. The outer layers of the star are blown into space, while the core is compressed into an incredibly dense object, like a neutron star or even a black hole, depending on the star's mass. The energy released in a supernova is so immense that it can outshine an entire galaxy. In fact, a single supernova can release more energy in a few seconds than our sun will produce over its entire 10 billion year lifespan. This explosion also hurls vast amounts of material into space, including heavy elements like gold, silver, and uranium. These elements are forged in the intense heat and pressure of the supernova, and they're scattered across the cosmos, eventually becoming part of new stars, planets, and even life. In a way, every atom of gold in your jewelry, every bit of iron in your blood, was once forged in the heart of a dying star. Supernovae are also vital to the universe in another way. They play a key role in spreading these heavy elements throughout the galaxy. Without supernova, the universe would be a much more basic place, filled mostly with hydrogen and helium. The explosions of stars enrich the interstellar medium, the space between stars, with the elements needed to form complex structures like planets, moons, and living organisms. In this sense, supernovae are not just the death of a star, but also a kind of cosmic recycling program, making new creation possible. But not all supernovae are the same. There are two main types, Type 1 and Type 2. Type 1 supernovae occur in binary star systems, where one of the stars is a white dwarf. Over time, the white dwarf pulls material from its companion star. When it accumulates enough mass, it can no longer support itself, and it explodes in a thermonuclear detonation. Type 2 supernovae, on the other hand, happen when a single massive star reaches the end of its life and undergoes core collapse, as we discussed earlier. One of the most famous supernovae in recent history is supernova 1987A, which exploded in a nearby galaxy called the Large Magellanic Cloud. It was the closest supernova to Earth in over 400 years, and its light reached us in 1987. This event provided astronomers with a unique opportunity to study a supernova up close and gain valuable insights into the death of stars. Even decades later, scientists continue to observe the remnants of supernova 1987A, learning more about the processes that occur in the aftermath of such an explosion. As you drift off to sleep, think of the stars above, each one a massive ball of gas, burning brightly in the dark expanse of space. Some of them are quietly living out their lives, while others may be nearing their explosive end, ready to go out in a blaze of glory. These cosmic fireworks are a reminder that even in death, there is creation. The universe is in a constant state of change, with stars being born, living their lives, and then, in their final act, giving back to the cosmos. Supernovae are the ultimate paradox of destruction and creation, a brilliant, fleeting moment that shapes the very fabric of the universe, the expanding universe. Imagine you're sitting on the edge of a massive field, watching distant balloons scattered across the grass. Now imagine that the balloons are slowly inflating. As they expand, each balloon grows larger, but something else happens too. The space between them stretches out. The field itself seems to be growing, pulling the balloons farther apart. This is an analogy for our expanding universe, where galaxies are like the balloons, and space itself is the field that's stretching. The galaxies aren't necessarily moving through space. Instead, space is expanding between them, pushing them apart. The idea of the expanding universe is one of the most profound discoveries in cosmology. For centuries, it was believed that the universe was static, unchanging, and eternal. But in the early 20th century, astronomers began to notice something strange. By studying the light from distant galaxies, they found that these galaxies were not stationary. Instead, they were moving away from us. And the farther away they were, the faster they were receding. This observation led to the groundbreaking realization that the universe is expanding. This discovery was made possible by the phenomenon of redshift. When an object moves away from an observer, the light it emits is stretched into longer wavelengths, shifting toward the red end of the spectrum. Think of the sound of a passing car. As it moves toward you, the pitch of the sound is higher, but as it moves away, the pitch drops. This is known as the Doppler effect, and it works similarly with light. When astronomers observed that the light from distant galaxies was redshifted, they realized those galaxies were moving away from us, carried by the expanding fabric of space. The expansion of the universe was first predicted by Albert Einstein's theory of general relativity. Einstein's equation suggested that the universe should be either expanding or contracting, but Einstein himself initially resisted the idea. He introduced a cosmological constant into his equations to keep the universe static, a decision he later called his biggest blunder. It wasn't until astronomer Edwin Hubble made his famous observations in the 1920s that the expansion of the universe was confirmed. Hubble's work showed that galaxies were receding from us in all directions, leading to the conclusion that the universe itself was growing larger over time. This discovery had profound implications for our understanding of the cosmos. If the universe is expanding, that means it must have been smaller in the past. Tracing this expansion backward in time leads to the concept of the Big Bang, a moment when the entire universe was condensed into an incredibly hot, dense point before exploding outward and expanding into what we see today. The expansion of the universe continues to this day, and it's happening on a massive scale. On smaller scales, gravity keeps objects like galaxies and solar systems bound together. But on cosmic scales, the expansion of space becomes dominant. One of the most surprising aspects of the expanding universe is that it's accelerating. In the 1990s, astronomers discovered that distant supernovae were dimmer than expected, suggesting that the expansion of the universe was speeding up. This was a shocking discovery because gravity, which pulls objects together, was expected to slow down the expansion over time. Instead, something mysterious was pushing the universe to expand faster and faster. This unknown force is called dark energy, and it makes up about 68% of the universe's total energy. Despite its significant presence, dark energy remains one of the biggest mysteries in cosmology. As the universe continues to expand, the distances between galaxies will grow larger, and the observable universe will shrink. Galaxies that are currently visible will eventually be pushed beyond the cosmic horizon, disappearing from our view forever. The night sky as we know it today will look very different billions of years from now, with fewer and fewer galaxies visible as the expansion accelerates. It's a sobering thought, but it also highlights the transient nature of our cosmic observation. So as you imagine those distant galaxies, think of them as ships drifting on an ever-expanding ocean, carried farther and farther away by the currents of space. The universe is not static. It's a dynamic, evolving entity, and we are just tiny observers floating along in its vast expanse. As you drift off to sleep, let the image of galaxies in motion remind you of the constant, subtle changes happening all around us, both in the universe and in our own lives. The expansion of the universe is a quiet, persistent force, one that carries the galaxies away in a slow, steady dance across the cosmic sea. The observable universe. Imagine standing on the shore of a vast ocean. The horizon stretches out endlessly before you, and while you can see the waves rolling in and out, there's no way to grasp the entire expanse. You know the ocean continues far beyond your line of sight, but from where you stand, you're only catching a tiny glimpse of something unimaginably larger. This is precisely what our view of the universe is like, an endless cosmic ocean with only a small portion visible to us, confined to what we call the observable universe. The observable universe represents the portion of the cosmos that we can see or measure with our instruments. It's like the visible waves on the ocean's surface, familiar, tangible, but ultimately only a fraction of the total. The distance we can observe is limited by the age of the universe and the speed of light. Since the universe is about 13.8 billion years old, the farthest light has had time to travel reaches us from about 13.8 billion light years away. However, because the universe is expanding, that light now comes from regions much farther than 13.8 billion light years. In fact, the edge of the observable universe is roughly 46.5 billion light years from us in every direction, creating an observable bubble with a diameter of about 93 billion light years. To put that in perspective, imagine trying to measure the distance between grains of sand on a beach, with a single grain representing our Milky Way galaxy. The observable universe contains around 2 trillion galaxies, each with hundreds of billions of stars, planets, and other celestial objects. Yet, despite these staggering numbers, this observable section is likely just a drop in the ocean compared to the entire universe. What lies beyond our view? That's one of the most intriguing questions in cosmology. Our view of the universe is constrained by the speed of light, which acts as a cosmic speed limit. Even if there are galaxies and stars beyond the observable universe, their light hasn't had enough time to reach us since the beginning of the universe. It's like standing in the middle of a dense forest, only able to see the trees immediately around you, while the rest remains shrouded in mystery. But what about those distant edges of the observable universe? As we look farther and farther away, we're also looking back in time. The light from galaxies billions of light years away began its journey billions of years ago. So when we observe these distant galaxies, we're not seeing them as they are today, but as they were billions of years ago. This means the observable universe is not only a look at what exists, but also a window into the history of the cosmos itself, a living record of the universe's evolution over time. Now, let's think about that vast expanse. Even if we could travel at the speed of light, it would take us billions of years to reach the farthest galaxies we can observe. And yet, despite this immense distance, the observable universe is only a fraction of the entire cosmos. Some cosmologists theorize that the entire universe could be infinitely large, meaning there's no end to the cosmic ocean we're peering into. Others suggest that the universe might have a defined shape, like a sphere or a donut, but still far larger than we can ever perceive. One of the most mind-bending aspects of the observable universe is that it's expanding. The space between galaxies is stretching, like dots on a balloon as it inflates. As this expansion continues, distant galaxies are moving away from us, and the light they emit is stretched into longer wavelengths, shifting into the red part of the spectrum, a phenomenon known as redshift. Eventually, some galaxies will move so far away that their light will never reach us, effectively disappearing from our observable universe. This leads to an unsettling thought. The observable universe is constantly shrinking in terms of the objects we can see. As time goes on, more and more of the cosmos will slip out of view, lost beyond the cosmic horizon, never to be seen again. The observable universe is like a candle flickering in the wind, bright and visible for now, but destined to fade into darkness over unimaginable timescales. So here we are, standing on the shore of the cosmic ocean, gazing out at the waves we can see, knowing there's so much more beyond the horizon. The observable universe is a profound reminder of both our knowledge and our limitations, a tiny piece of a grander whole that remains, for now, hidden from our view. As you drift off to sleep, let the vastness of the universe surround you, reminding you that even in the immensity of the cosmos, there's still so much to discover and understand. Causality. Causality, the principle that every effect has a cause, is one of the fundamental concepts underpinning our understanding of the universe. This principle is so ingrained in our perception of reality that it can be challenging to imagine a world where cause and effect do not operate in harmony. To unravel the complexity of causality, let's embark on a journey through the cosmos, exploring the deep connections between cause and effect, from the subatomic to the cosmic scale. Imagine for a moment the universe as a grand symphony. Each note played by the orchestra represents an event, and every event has a cause, much like how a melody is shaped by the instruments and their interplay. In this symphony, causality is the conductor, guiding the flow from one note to the next, ensuring a coherent and harmonious composition. Without this conductor, the symphony would devolve into chaos, each note disconnected from the next, devoid of meaning and structure. At the most microscopic level, causality governs the interactions between particles. Consider the behavior of electrons in an atom. According to quantum mechanics, particles like electrons do not have definite positions or velocities until they are observed. This uncertainty, however, does not imply a breakdown in causality. Instead, it reveals a more nuanced version of cause and effect. The probabilistic nature of quantum mechanics suggests that while the exact state of a particle is uncertain, the overall probabilities and statistical outcomes adhere to a deterministic framework. This duality showcases causality's adaptability and resilience across different scales of reality. Now, shift your focus to the grand stage of the universe, where causality manifests in the cosmic dance of celestial bodies. Take the example of a star's life cycle, from its birth in a nebula to its death as a supernova. Each phase of a star's life is a result of specific causes: the accumulation of gas, nuclear fusion, and gravitational forces. The death of a star as a supernova, in turn, creates elements that are crucial for the formation of new stars and planets. This process exemplifies causality on a cosmic scale, where every stage is intricately linked to preceding and succeeding stages, creating a continuous and evolving cosmic narrative. Causality is not just a passive observer in this grand cosmic narrative. It actively shapes the structure and evolution of the universe. For instance, the theory of general relativity, proposed by Albert Einstein, reveals how massive objects like stars and planets warp the fabric of space-time. This warping is not merely a backdrop, but a dynamic participant in causality. It dictates how objects move and interact, illustrating how fundamental forces and objects influence each other in a constantly evolving cosmic ballet. The concept of causality also extends to the very fabric of reality itself. In cosmology, the Big Bang theory posits that the universe began from an extremely hot and dense state, approximately 13.8 billion years ago. The singular event, the cause, set in motion the expansion and cooling that led to the formation of galaxies, stars, and planets. The progression from the Big Bang to the present day exemplifies a causal chain, where each step is the effect of the previous stage and the cause of the next. Yet, the concept of causality is not without its paradoxes and mysteries. One of the most intriguing aspects is the notion of causality in the context of time.
If we imagine time as a linear progression from past to future, causality seems straightforward. However, theories such as those involving wormholes or time travel introduce scenarios where cause and effect might not follow the conventional order. For example, if one could travel backward in time, it raises questions about the possibility of altering past events and creating paradoxes where effects precede their causes. These theoretical possibilities challenge our understanding of causality and provoke deep philosophical inquiries about the nature of time and reality. In summary, causality is the thread that weaves together the fabric of the universe, from the interactions of subatomic particles to the grand choreography of cosmic events. It ensures that every effect is rooted in a cause, creating a coherent and interconnected reality. As we explore deeper into the mysteries of the universe, we encounter both the elegance and the enigma of causality, revealing a dynamic interplay that shapes the structure and evolution of everything around us. In the grand symphony of the cosmos, causality remains the enduring conductor, guiding each note and ensuring the harmony of existence. Gamma ray, part gamma ray bursts, cosmic beacons of destruction in the vast theater of the cosmos. Gamma ray bursts, GRBs, are among the most dramatic and enigmatic phenomena, illuminating the universe with a brief but intense flare of energy. These cosmic beacons of destruction are the universe's most powerful explosions, releasing more energy in a few seconds than the sun will emit over its entire lifetime. To truly grasp the significance of gamma-ray bursts, one must delve into the heart of these cataclysmic events, exploring their origins, impacts, and the profound insights they offer about the universe. Imagine the universe as a vast, dark ocean. Occasionally, an enormous unseen force within this ocean triggers a cataclysmic eruption, sending a blinding flash of light across the cosmos. This is a gamma-ray burst, a flash so intense that it momentarily outshines all the stars in its host galaxy combined. To put it in perspective, if you were to observe a gamma-ray burst from a nearby galaxy, its energy would be comparable to the total output of our sun over billions of years, compressed into a fraction of a second. Gamma-ray bursts were first detected in the 1960s by the military satellites designed to monitor nuclear tests. These bursts of gamma rays, high-energy electromagnetic radiation, were so intense and unexpected that they initially confounded scientists. The discovery of these bursts led to a new chapter in astrophysics, unveiling a cosmic phenomenon that was as elusive as it was powerful. The origins of gamma-ray bursts can be traced to some of the most violent processes in the universe. There are two primary types of GRBs, classified based on their duration and progenitor events. Long-duration GRBs, which last more than 2 seconds, are believed to result from the collapse of massive stars into black holes. This process, known as a supernova or hypernova, involves the complete gravitational collapse of the star's core, leading to the formation of a black hole and an accompanying burst of gamma rays. The accompanying explosion ejects massive amounts of energy and matter into space, sometimes forming a relativistic jet that emits gamma rays. In contrast, short duration bursts, lasting less than 2 seconds, are thought to originate from the collision of neutron stars or the merger of neutron stars and black holes. These events result in the rapid coalescence of dense objects, leading to intense gravitational interactions and the ejection of gamma rays. The discovery that both types of GRBs are linked to stellar remnants has provided crucial insights into the life cycles of stars and the formation of black holes. The impact of a gamma-ray burst on its surroundings can be profound. The intense gamma rays emitted during a GRB can ionize interstellar gas and dust,
potentially affecting star formation in its host galaxy. If a GRB occurs within our galaxy, its radiation could have significant consequences for Earth. While the probability of such an event happening within our cosmic neighborhood is low, the potential for disruption is significant. A nearby GRB could theoretically strip away the Earth's atmosphere or affect the biosphere, triggering mass extinctions or altering the climate. On a grander scale, gamma-ray bursts provide a unique window into the distant universe. Because they are so luminous, GRBs can be observed across vast distances, allowing astronomers to probe the early stages of the universe's evolution. By studying the light curves and afterglows of GRBs, scientists can glean information about the conditions in the early universe, the formation of the first black holes, and the nature of the interstellar medium. Moreover, gamma-ray bursts have also been instrumental in advancing our understanding of relativistic jets, highly collimated streams of particles moving at nearly the speed of light. These jets, ejected during a GRB, can be observed in the form of afterglows across various wavelengths, including X-rays, optical, and radio. The study of these jets has revealed much about the mechanisms behind the formation of GRBs and the conditions necessary for their occurrence. In essence, gamma-ray bursts are cosmic beacons of destruction, illuminating the universe with their transient yet astonishingly powerful flashes. They are reminders of the universe's dynamic nature, where colossal forces shape the fabric of reality and drive the evolution of galaxies. Each gamma-ray burst is a fleeting spectacle of cosmic violence, offering a glimpse into the most extreme processes known to science. As we continue to unravel the mysteries of these extraordinary events, we gain deeper insights into the universe's complex and ever-changing natura, revealing the profound and often awe-inspiring mechanisms that govern the cosmos. Vacuum decay. In the realm of theoretical physics, few concepts provoke as much existential intrigue as vacuum decay. This enigmatic idea delves into the possibility that the very fabric of our universe might be unstable, subject to a cataclysmic transformation that could alter the fundamental nature of reality itself. To explore vacuum decay is to journey into the heart of cosmic instability and the ultimate fragility of the universe's structure. Imagine the universe as a vast, tranquil lake. Its surface is perfectly smooth, reflecting the celestial dome above. This surface represents the current state of the vacuum, a seemingly stable and smooth backdrop against which the cosmic drama unfolds. But what if beneath this serene surface lay a turbulent maelstrom, an underlying instability, ready to erupt and disrupt the calm? This turbulence is what theoretical physicists describe as vacuum decay, a potential scenario where our universe might suddenly transition to a lower energy state, fundamentally altering its properties. At the core of vacuum decay is the concept of the vacuum state in quantum field theory. In this context, the vacuum is not an empty void, but rather a complex, dynamic field with its own energy levels and potential states. The current vacuum state of our universe is thought to be in a metastable condition, like a ball resting in a valley on a potential energy landscape. While it seems stable, it is not necessarily the lowest possible energy state. The notion of vacuum decay arises from the idea that this current vacuum state could be a local minimum in the energy landscape, rather than the absolute minimum. Picture a ball resting in a shallow dip in a rolling hill. While it appears stable, there is always a possibility that it might roll down to a deeper valley, experiencing a dramatic shift in its surroundings. Similarly, if our universe were to transition to a lower energy vacuum strata, it would be akin to the ball rolling into a deeper valley with potentially catastrophic consequences.
This transition or vacuum decay would occur at the speed of light, propagating outward from a point of instability. The resulting change in the vacuum state would alter fundamental constants and forces, such as the strength of gravity, the charge of particles, or the behavior of fundamental interaction. Such a transition would likely annihilate the existing structure of the universe, obliterating everything as we know it in an instant. The transformation would be so profound that any matter and energy in the affected region would be reconfigured into a new state of existence, or potentially annihilated altogether. To illustrate the potential effects of vacuum decay, consider the universe as a massive and complex machine, with each part precisely tuned to ensure smooth operation. A sudden malfunction or reconfiguration of one component could send shockwaves through the entire system, disrupting or destroying the machinery. Similarly, a vacuum decay event would alter the fundamental parameters of our universe, rendering the current laws of physics obsolete and possibly leading to a chaotic restructuring of reality. Despite the dramatic implications of vacuum decay, it remains a speculative scenario. Current scientific understanding suggests that the vacuum status of our universe is stable enough to sustain its observed properties over cosmological timescales. However, the possibility of vacuum decay underscores the inherent uncertainty in our understanding of the universe's fundamental nature. It highlights the need for ongoing research in theoretical physics and cosmology to probe the stability of our vacuum state and refine our knowledge of the underlying principles governing the universe. The concept of vacuum decay also raises profound philosophical questions about the nature of reality and our place within it. It challenges our perceptions of cosmic stability and invites us to contemplate the limits of our knowledge. Are we merely inhabitants of a transient, metastable universe, subject to sudden and unpredictable shifts in fundamental properties? Or is our understanding of vacuum stability sufficiently robust to reassure us of a long-lasting cosmic order? In summary, vacuum decay represents a fascinating and unsettling possibility in the landscape of theoretical physics. It embodies the idea that our universe, despite its apparent stability, could be subject to a sudden and dramatic transformation that alters the very essence of reality. This concept serves as a reminder of the profound and sometimes unsettling nature of cosmic science, urging us to explore the deepest mysteries of the universe with both curiosity and humility. As we continue to investigate the fundamental forces and structures of our cosmos, we gain deeper insights into the potential vulnerabilities and resilience of the universe, enriching our understanding of the complex and ever-evolving nature of existence. Cosmic inflation. In the grand saga of the cosmos, there exists a chapter of extraordinary rapidity and expansion, known as cosmic inflation. This pivotal period in the universe's early history transformed the cosmos from a microscopic speck into the vast expanse we observe today. To grasp the profound implications of inflation, let's venture into this crucial phase of the universe's evolution, where the very fabric of reality underwent a spectacular growth spurt. Imagine, if you will, the universe as an enormous, intricate balloon. In the beginning, this balloon is deflated to an almost imperceptible size, filled with a dense, primordial fog. This minuscule balloon represents the early universe, teeming with potential, but constrained by its tiny volume. Cosmic inflation is akin to an explosive breath of air, causing the balloon to expand exponentially, stretching its surface rapidly and uniformly. This breath of air represents the inflationary force that drove the universe's remarkable growth during its infancy. Cosmic inflation, proposed by Alan Guth in the early 1980s, posits that the universe underwent a period of extraordinarily rapid expansion shortly after the Big Bang. This phase of inflation is thought to have occurred within the first fraction of a second of the universe's existence. During this brief yet intense period,
the universe expanded at a rate many times faster than the speed of light, growing from subatomic, scaleless to vast, observable dimensions. This growth was not merely a stretching of space, but an intricate reshaping of the universe's structure. To visualize this, consider a balloon with a grid drawn on its surface. As the balloon inflates, the grid lines stretch apart, increasing the distance between any 2 points on the balloon's surface. Similarly, during cosmic inflation, the fabric of space itself stretched, increasing the distances between regions of matter and energy. This stretching not only enlarged the universe, but also smoothed out irregularities and homogenized its structure, laying the groundwork for the formation of galaxies and cosmic structures. One of the key motivations for the inflationary theory is its ability to address several puzzles of the Big Bang model, such as the horizon problem and the flatness problem. The horizon problem refers to the observation that distant regions of the universe, seemingly disconnected by vast distances, have remarkably uniform temperatures and properties. Inflation solves this by proposing that these regions were once close together, before being stretched apart, explaining their uniformity. The flatness problem arises from the observation that the universe appears to be very close to spatially flat, with a critical density that makes the geometry of the universe almost perfectly Euclidean. Inflation addresses this by suggesting that any initial curvature was smoothed out during the rapid expansion, resulting in the nearly flat universe observed today. During the inflationary epoch, quantum fluctuations in the primordial field responsible for inflation, often referred to as the inflaton field, gave rise to tiny density variations. These quantum fluctuations were magnified by the rapid expansion, seeding the formation of large-scale structures such as galaxies and clusters of galaxies. To use an analogy, imagine a calm pond where a stone is thrown. The ripples created by the stone's impact spread outwards, eventually forming waves that shape the pond's surface. Similarly, sequential fluctuations during inflation que cosmic ripple effects as well above the large scale structures observed in the universe. And inflation also has profound implications for the study of cosmic microwave background, CMB radiation, the afterglow of the Big Bang. Observations of the CMB provide a snapshot of the universe's infancy, revealing the remnants of the early inflationary period. The uniformity and slight variations in the CMB temperature across the sky serve as a cosmic fossil record of inflation, offering a direct observational probe into this crucial epoch. In summary, cosmic inflation represents one of the most transformative and profound episodes in the universe's history. It marks a period when the cosmos experienced an extraordinary growth spurt, expanding from an infinitesimal point to the vast, structured universe we see today. Inflation not only addresses fundamental questions about the early universe, but also lays the groundwork for understanding the formation of cosmic structures and the uniformity of the universe. As we continue to explore and refine our understanding of inflation, we gain deeper insights into the universe's origins and its remarkable journey from a primordial fog to the intricate and expansive cosmos we inhabit. Fermi Paradox. In the quest to understand our place in the universe, the Fermi Paradox stands as one of the most profound and perplexing questions in modern science. Named after the physicist Enrico Fermi, the paradox emerges from a simple yet profound observation. Given the vast number of stars and potentially habitable planets in the galaxy, and the age of the universe, why have we not yet detected any signs of extraterrestrial civilizations? To explore this paradox, we must delve into the vastness of the cosmos and the myriad of possibilities that could explain this cosmic silence. Picture the Milky Way galaxy as a bustling, star-studded metropolis, each star a potential hub of activity. Within this metropolis, the possibilities for life seem nearly endless. If we assume that advanced civilizations are not just possible but likely, then we would expect to encounter numerous signs of their existence, whether through direct contact, technological signals, or other forms of evidence. Yet, despite our extensive efforts and the vastness of our observational reach, We have not encountered any clear indications of extraterrestrial life. This discrepancy between expectation and reality forms the crux of the Fermi paradox. To grasp the scale of the paradox, consider the following analogy. Imagine you are a detective in a vast, sprawling city with numerous neighborhoods. You know that crimes are happening all over the city. But despite your extensive investigation and the use of advanced surveillance technology, you find no evidence of these crimes. You know the crimes must be occurring based on statistical probabilities and witness accounts. Yet your investigations yield no results. This is akin to our search for extraterrestrial life. Given the high probability of its existence, a lack of evidence feels both perplexing and unsettling. Several key factors contribute to the Fermi paradox. First is the sheer number of stars and planets in the galaxy. The Milky Way alone contains over 100 billion stars, many of which have planets in the habitable zone where life could potentially arise. Given these odds, it seems statistically improbable that Earth is the only planet with intelligent life. Moreover, the universe is approximately 13.8 billion years old, providing ample time for advanced civilizations to emerge and potentially colonize the galaxy. In theory, even slow-moving civilizations could have spread across the galaxy in a few million years. However, several potential solutions to the Fermi paradox offer different explanations for the silence we observe. One possibility is the rare Earth hypothesis, which suggests that while simple life may be common, complex, intelligent life is exceedingly rare. This hypothesis posits that Earth's unique combination of conditions, including its stable climate, magnetic field, and geological activity, might be exceptionally rare in the galaxy. Thus, the development of advanced civilizations could be an extraordinary anomaly rather than a common occurrence. Another possibility is the Great Filter theory. The Great Filter hypothesis proposes that at some stage of development, civilizations encounter significant barriers that prevent them from advancing to the point of interstellar communication or travel. These barriers could be any number of challenges such as self-destruction through warfare, environmental collapse, or technological stagnation. If the Great Filter is ahead of us, it implies that our future might be more precarious than we currently anticipate. Conversely, if the filter lies behind us, it suggests that the emergence of intelligent life is incredibly rare, and that we have already surpassed the most challenging obstacles. The zoo hypothesis offers a different perspective, proposing that advanced extraterrestrial civilizations are aware of us, but deliberately choose not to make contact. This hypothesis likens our situation to that of animals in a zoo, where advanced beings observe us from a distance, ensuring that their presence does not interfere with our natural development. This scenario suggests that extraterrestrial civilizations may be adhering to a principle of non-interference, akin to a cosmic version of the Prime Directive from Star Trek. Another intriguing possibility is that advanced civilizations may use communication methods beyond our current technological capabilities. For instance, they might utilize advanced forms of communication that are beyond our current understanding, such as quantum entanglement or higher dimensional signals. In this case, the silence could be due to our inability to detect or interpret their messages rather than their absence. Lastly, the transient nature of civilizations hypothesis proposes that civilizations might have short-lived technological periods. Advanced civilizations could emerge, develop technology, and then collapse or evolve beyond recognition before we have a chance to detect them. This transient nature could mean that the window of time during which civilizations are detectable is relatively brief in cosmic terms. In conclusion, the Fermi paradox encapsulates one of the most intriguing and enigmatic questions in our search for extraterrestrial life. Despite the vastness of the galaxy and the high probability of habitable planets, the absence of detectable extraterrestrial civilizations challenges our understanding of life in the universe. Whether the solution lies in the rarity of intelligent life, the barriers imposed by the Great Filter, the deliberate silence of advanced civilizations, or our current technological limitations, The paradox continues to drive our exploration and deepen our curiosity about our place in the cosmic tapestry. As we advance our technology and extend our reach, we may yet uncover answers that will reshape our understanding of life and our role in the vast expanse of the universe. Great filter. In the quest to solve the Fermi paradox, the perplexing question of why we haven't detected extraterrestrial civilizations despite the vastness of the galaxy, one of the most intriguing and unsettling concepts is the Great Filter. This theory posits that there may be a significant barrier or series of barriers that prevent the emergence of advanced civilizations. To explore the Great Filter is to confront the possibility that the universe's silence might be a sign of a daunting and universal obstacle that is either behind us or ahead of us. Imagine a grand cosmic relay race where civilizations are the runners, each striving to reach the finish line of interstellar communication or space colonization. In this race, there are numerous hurdles scattered along the track, some small, some colossal. The Great Filter represents these hurdles, and the fact that we haven't encountered any. Other runners could mean that these obstacles are either extremely challenging or that very few runners have made it past them. The Great Filter provides a framework for understanding why, despite the vast number of stars and planets, we might not yet have encountered any other advanced civilizations. The concept of the Great Filter was first proposed by economist Robin Hanson in the early 1990s. It aims to address the discrepancy between the high probability of extraterrestrial civilizations and the apparent absence of any detectable signs of them. The theory suggests that at some stage in the development of life, a significant and nearly insurmountable barrier exists that drastically reduces the number of civilizations that could potentially advance to the point of interstellar communication. To better grasp the Great Filter, consider the following analogy. Imagine a vast ancient library with countless shelves, each filled with books representing potential pathways for the emergence of intelligent civilizations. The library is enormous, and each book represents a possible stage in the evolution of life and intelligence. Some books are filled with complex narratives and profound discoveries, while others are blank or contain tales of civilizations that never progressed beyond a primitive state. The Great Filter is akin to the blank pages or the books that are missing altogether, indicating that something crucial is preventing many civilizations from making it past certain developmental milestones. One possible location for the Great Filter is before the emergence of complex life. The early stages of life on Earth, from simple single-celled organisms to complex multicellular entities, were fraught with challenge. The transition from chemical processes to self-replicating life forms must be exceedingly rare. If the Great Filter exists at this stage, it would imply that the leap from non-living chemistry to living organisms is an extraordinarily rare event, making the existence of complex life forms like ourselves a rare occurrence in the cosmos. Alternatively, the Great Filter might be located at a more advanced stage in the development of civilization. For instance, the transition from technological development to the capability for interstellar communication or travel might be fraught with obstacles. Advanced civilizations could face existential risks that lead to self-destruction, such as nuclear war, environmental collapse, or technological mishaps. If the Great Filter lies at this stage, it suggests that the ability to survive and thrive as a technologically advanced species is exceptionally rare. Another intriguing possibility is that the Great Filter lies ahead of us,
If we are on a trajectory that includes a future great filter, it implies that we may face significant challenges or threats that could prevent us from reaching advanced stages of space exploration or communication. These future obstacles could include resource depletion, climate change, or unforeseen technological dangers. In this scenario, the silence of the cosmos could serve as a cautionary signal, urging us to address these potential risks to ensure our survival and continued development. The Great Filter theory raises profound implications for our understanding of the universe and our place within it. If the filter is behind us, it highlights the rarity of advanced civilizations and the exceptional nature of our existence. If the filter is ahead of us, it underscores the importance of addressing existential risks and making conscious efforts to mitigate potential threats. Ultimately, the Great Filter serves as both a challenge and an opportunity. It challenges our assumptions about the prevalence of intelligent life and reminds us of the potential fragility of our own civilization. It also provides an opportunity for reflection and action, encouraging us to explore ways to overcome potential barriers and ensure the longevity of our technological and societal advancements. In summary, the Great Filter offers a compelling solution to the Fermi paradox by suggesting that significant barriers exist at various stages of civilization development, limiting the number of advanced civilizations we might encounter. Whether the filter is located in our past or our future, it provides a framework for understanding the cosmic silence and motivates us to address potential challenges as we continue our quest for knowledge and exploration. As we navigate the complexities of our existence and seek to expand our horizons, the Great Filter remains a powerful concept that shapes our understanding of the universe and our role within it. Kardashev Scale. In the quest to understand the potential for advanced extraterrestrial civilizations, the Kardashev Scale offers a framework to quantify and categorize the technological and energy harnessing capabilities of such societies. Developed by the Russian astrophysicist Nikolai Kardashev in 1964, this scale provides a method for measuring the advancement of civilizations based on their energy consumption. To explore the Kardashev scale is to delve into the possibilities of how civilizations might harness energy and evolve as they reach for the stars. Imagine the universe as a grand stage where civilizations perform their technological dramas. On this stage, the Kardashev scale serves as a set of curtains that help us reveal the level of sophistication and power each civilization wields. The scale is divided into 3 primary types, each representing a different level of energy consumption and technological prowess. This type S, ranging from type A on to type 3, offer insights into how advanced civilizations might harness and utilize the resources available to them. Type A civilization, planetary scale. A Type 1 civilization, sometimes referred to as a planetary civilization, is capable of harnessing all the available energy resources on its home planet. Imagine a civilization that has mastered the art of tapping into geothermal, solar, wind, and hydroelectric power, optimizing its technological infrastructure to exploit every ounce of energy produced by the planet's natural processes. Such a civilization would have achieved a harmonious balance with its environment. To illustrate this concept, Cinco Pasha such an interconnected machine engineer who has perfected every aspect of this machine, ensuring that every cog, wheel, and lever operates at peak efficiency. This civilization would be capable of controlling weather patterns, managing planetary resources, and even influencing geological processes to some extent. While humanity is not yet a Type 1 civilization, we are on the path toward achieving this status as we continue to develop and implement advanced energy technologies. Type 2 Civilization. Stellar scale. A Type 2 civilization extends its reach beyond its home planet to harness the energy output of its entire star. This type of civilization is often described as stellar or solar, reflecting its ability to capture and utilize the immense power generated by its star. Imagine a civilization that constructs a Dyson sphere, a hypothetical megastructure, around its star to capture and store a significant portion of its energy output. This energy could then be used to power advanced technologies, enable interstellar travel, and support a vastly expanded population. Visualize a type 2 civilization as an architect capable of building a colossal energy harvesting apparatus that envelops the entire star, harnessing its radiant energy for various purposes. Such a civilization would possess the technology to manipulate stellar processes and potentially even manage the star's life cycle. The construction of a Dyson sphere, though speculative, exemplifies the immense scale and ambition of a Type 2 civilization's energy endeavors. Type 3. Civilization, galactic scale. A Type 3 civilization represents the pinnacle of technological advancement, harnessing the energy output of an entire galaxy. This type of civilization would have achieved mastery over the energy resources of billions of stars, allowing it to conduct activities on a galactic scale. Envision a civilization that has the ability to control and utilize the energy of entire star systems, manipulate stellar dynamics, and potentially even influence galactic events. To conceptualize a Type 3 civilization, imagine a cosmic engineer capable of managing the power and resources of an entire galaxy. This civilization might be able to construct enormous structures such as Dyson swarms, collections of individual solar collectors, or even engage in large-scale engineering projects that impact the galaxy as a whole. The ability to manipulate galactic-scale energy would provide unprecedented opportunities for exploration, colonization, and technological innovation. Beyond Type 3, theoretical extensions. Beyond the Type 3 civilization, some theorists speculate about civilizations that might harness the energy of multiple galaxies or even the entire universe. These hypothetical civilizations, often referred to as Type 4 or Type 5, would be capable of manipulating cosmic phenomena and leveraging energy on an even grander scale. While these ideas remain speculative, they offer intriguing possibilities for the future of civilization and its potential evolution. In summary, the Kardashev scale provides a valuable framework for understanding the potential capabilities and energy requirements of advanced civilizations. By categorizing civilizations into Type 1, 2, and 3, the scale offers insights into how societies might evolve and harness energy on different levels. From the mastery of planetary resources to the manipulation of stellar and galactic energy, the Kardashev scale helps us imagine the grand possibilities of technological advancement and the future of civilization. As we continue to explore the universe and develop our own technologies, the Kardashev scale remains a guiding star, illuminating the path toward understanding the potential scope and scale of intelligence live beyond our own world. Dison Speres. In the pursuit of understanding how advanced civilizations may harness cosmic energy, the concept of Dyson spheres stands out as one of the most imaginative and ambitious ideas, proposed by the physicist and mathematician Freeman Dyson in 1960. Dyson spheres offer a vision of how an advanced civilization could capture the immense energy output of its star. This concept not only stretches the boundaries of our imagination, but also provides a fascinating glimpse into the potential future of energy utilization and technological development. Picture the sun as a vast, radiant furnace, radiating energy into the cosmos in every direction. This energy, while abundant, is dispersed over an immense area, making it challenging to harness efficiently. Dyson's proposal offers a solution to this challenge by envisioning a series of megastructures designed to capture and utilize a significant portion of a star's energy. To better understand Dyson spheres, let us embark on a journey through this grand concept, exploring its implications and the technological marvels it represents. The concept of Dyson spheres.
The Dyson sphere is often visualized as a colossal shell or array of structures surrounding a star, designed to capture and channel its energy output. Dyson initially proposed a simpler concept, a Dyson swarm, a collection of individual solar collectors orbiting the star in a manner akin to planets orbiting a sun. These collectors would gather solar energy and transmit it back to the civilization, providing a nearly limitless supply of power. Imagine the sun as a grand cosmic lighthouse, its beams shining across the galaxy. A Dyson swarm would be akin to an enormous fleet of solar panels orbiting this lighthouse, capturing its light and converting it into usable energy. Each panel, while individually small, would collectively gather an enormous amount of energy, far exceeding what could be captured by a single planet-based technology. The Dyson shell. The Dyson shell, an extension of the Dyson swarm concept, represents an even more ambitious vision. In this model, the civilization constructs a solid, continuous shell around the star, completely encircling it. The shell would intercept the star's energy output, converting it into usable power. The structure would be an engineering marvel of unprecedented scale, requiring materials and technology beyond our current capabilities. Visualize the Dyson shell as an enormous, spherical structure surrounding the sun, with its surface covered in energy-harvesting panels. The shell would capture the star's energy more efficiently than a swarm of individual collectors, but the engineering challenges are immense. The construction of such a shell would involve overcoming significant obstacles, including the immense scale of the project, the need for vast quantities of materials, and the challenge of maintaining structural integrity in the face of gravitational forces. Technological and engineering considerations. The concept of Dyson spheres, while captivating, raises numerous technological and engineering questions. Constructing a Dyson shell would require advanced materials capable of withstanding extreme temperatures and radiation. Additionally, the structural integrity of such a shell must be maintained against gravitational forces, which could potentially destabilize the structure. A more feasible approach might be to develop a Dyson swarm, a collection of autonomous solar collectors orbiting the star. This approach avoids some of the challenges associated with constructing a solid shell and allows for more flexibility in terms of placement and configuration. A Dyson swarm could be deployed incrementally, with additional collectors added over time as technology advances. Implications for advanced civilizations. For an advanced civilization capable of constructing a Dyson sphere, the implications are profound. Harnessing the energy output of an entire star will provide an almost limitless supply of power, enabling the civilization to undertake a grand technological projects, explore distant star systems, and potentially even manipulate stellar processes. The ability to capture such vast amounts of energy would also have significant impacts on the civilization's development. With access to nearly limitless power, the civilization could develop advanced propulsion systems for interstellar travel, create artificial environments on a grand scale, and even engage in large-scale engineering projects, such as stellar engineering or galactic-scale megastructures. Search for extraterrestrial intelligence. The search for Dyson spheres also has implications for the search for extraterrestrial intelligence. SETI. Detecting a Dyson sphere or a Dyson swarm would be a powerful indicator of an advanced civilization. Such structures would likely emit waste heat and other signatures detectable across interstellar distances. The search for these signatures remains a crucial aspect of SETI, as it provides a means to identify potential advanced civilizations capable of harnessing stellar energy. In summary, Dyson spheres represent one of the most ambitious and imaginative concepts for harnessing cosmic energy. Whether envisioned as a Dyson swarm or a Dyson shell, these megastructures offer a glimpse into the potential future of advanced civilizations and their ability to capture and utilize the immense power of their stars. While constructing such structures remains a distant dream, the concept inspires us to explore new frontiers in energy technology and engineering as we continue to investigate the possibilities of Dyson spheres. we gain a deeper appreciation for the potential scale and scope of technological advancement and its implications for our understanding of the cosmos. Holographic principle. In the vast expanse of theoretical physics, few ideas challenge our perception of reality as profoundly as the holographic principle. This concept, which emerged from the fringes of string theory and black hole physics, suggests that our entire universe might be a holographic projection, a vast, three-dimensional illusion projected from information encoded on a distant, two-dimensional surface. To explore this principle is to embark on a journey through the nature of reality itself, challenging our deepest intuitions about the fabric of the cosmos. The genesis of the holographic principle. The holographic principle has its roots in the study of black holes, particularly the work of physicist Gerard 't Hooft and later Leonard Susskind in the 1990s. The principle arose from attempts to resolve paradoxes related to black hole information and entropy. Black holes, as described by general relativity, are regions of space where gravity is so intense that nothing can escape, not even light. However, the laws of quantum mechanics imply that information about the matter that falls into a black hole should not be lost, but rather encoded in some form on the black hole's event horizon, the boundary beyond which nothing can return. To visualize this, imagine a black hole as a cosmic sponge that absorbs everything around it. According to the holographic principle, all the information about the objects that have fallen into the black hole is not lost, but rather encoded on the surface of this sponge. The idea is that the information is not contained in the three-dimensional space inside the black hole, but rather on the two-dimensional surface of the event horizon. This insight led to the broader realization that the same might be true for the universe itself. Our three-dimensional reality could be a projection from a two-dimensional surface. The concept of holography. To understand the holographic principle, it helps to grasp the concept of holography itself. A hologram is a two-dimensional image that encodes three-dimensional information. When viewed under the right conditions, a hologram appears as a three-dimensional object. This means that all the three-dimensional information is contained within the two-dimensional surface of the hologram. The principle extrapolates this idea to the entire universe, suggesting that our three-dimensional reality is like a hologram projected from a two-dimensional boundary. Imagine a complex three-dimensional object, a sculpture, for instance. If we were to encode all the information about this sculpture onto a flat, two-dimensional film, we could reconstruct the entire three-dimensional form of the sculpture by shining light through the film. Similarly, according to the holographic principle, our universe might be a projection of information encoded on a distant cosmic surface. Implications for understanding the universe. The holographic principle has profound implications for our understanding of space, time, and the nature of reality. If our universe is indeed a hologram, then space and time as we perceive them might be emergent properties arising from the underlying two-dimensional surface. This shifts the focus of physical theories from the three-dimensional space we experience to a more abstract, lower-dimensional framework. One of the most intriguing aspects of the holographic principle is its potential to unify various theories of physics. It provides a way to reconcile general relativity, which describes gravity and the structure of space-time, with quantum mechanics, which governs the behavior of particles on the smallest scales. The principle suggests that the information governing the behavior of particles and forces might be encoded on a cosmic boundary, providing a new perspective on the fundamental nature of the universe. Testing the holographic principle. Testing the holographic principle is a formidable challenge. It requires understanding whether the principle's predictions align with observable phenomena and whether it can be integrated into existing theories. One approach involves studying black holes and their entropy, as these objects are natural laboratories for testing the principle. Researchers also explore the principle's implications for cosmology, string theory, and quantum gravity.